Hello everyone, so today I wanted to show you a brief tutorial on how to accept or reject a hypothesis using critical values and how to find those critical values using Microsoft Excel. So just kind of at a high level, the way you can think about these critical values is that we're comparing two things. One, a critical value, to a Z or T test statistic. So what's going on is that if we have an upper-tailed test, meaning that in our hypothesis setup, our alternative hypothesis, it has a greater than symbol in it, so we're dealing with a one-tailed test here, then we are talking about that right side of the bell-shaped curve that you can see, where if we have a Z or T test statistic and it ends up greater than that critical value, we fall into this big rejection region right here, like this whole area right here, meaning that we would reject it. So if it's on the upper tail, we're looking on the right side, and in order to fall into that region, the Z or T actually has to be greater than the critical value to end up in that region. On the other hand, if we're dealing with a lower tailed test, you can see that we're talking about the left side of the bell-shaped curve over there, where the critical value is this left side over there. And so when we compare our Z or T against the critical value, in order to fall into that rejection region, we actually have to be less than that critical value to end up in that section right there. So it's a lower tailed test if the alternative hypothesis says less than, and so in that case, the Z or T test statistic would have to be less than the critical value to fall in that region, which would decide we reject it. So that's how you decide if you accept or reject it, by comparing the two. But to actually find those numbers, it's a whole different story. So let's talk about that real quick. So to find the critical value in the first place, I'm about to show you a chart real quick, and that chart's going to drill down the logic you use in order to find out the Microsoft Excel function to use to find the critical value. So what that looks like is this chart right here. So I'd greatly recommend writing this down, maybe screen cap it to have it tucked to the side. But essentially, you start off by asking yourself, do we have a one-sided test or a two-sided test? A one-sided critical value or two-sided critical value? Well, that would just deal with whether or not it's a one-tailed test or a two-tailed test. So you can identify that. Essentially, a two-tailed is going to say equal to, not equal to, whereas a one-tailed test is going to show a greater than, less than. So you identify that first and look at the associated chart. Ask yourself whether or not it's a Z test or a T test, and we'll discuss on how to find that out in just a second. But you find that out first, drill down, and if it's Z test, don't look at the T test stuff anymore. You're just focused on Z test now because we're drilling it down. Ask yourself on the alternative hypothesis, so the HA, what is the setup on that? So if it's alternative on a two-sided critical value, it's going to look the same no matter what. It's going to say not equal to. However, if it's a one-sided critical value, you have to be careful to make sure you're looking at the alternative hypothesis, put down whether or not it's greater than, less than, and follow that instead. Finally, that will lead you to the critical value Excel function you use. You literally just plug right into that function and it will spit out the critical value for you. So there's a lot of different formulas for the critical value based on which kind of section you drill down into, but we'll go through one example towards the end to kind of show you how you do that. So let's go back here. So we have, just to find the critical value, we're using that chart completely. So then that asks, how do we find the test statistic? So essentially for these types of problems, we're dealing with either a Z or a T test statistic. So if we have a mean-based problem, meaning that we're just dealing with an average value, a mean number, nothing to do with a proportion where we have a part out of a whole, we're talking about some percent of a group that we're interested in, we're actually talking about numbers here, average numbers, then it's going to be a Z test if we do know the population standard deviation, and a T test if we do not know the population standard deviation. But for a proportion-based problem where we are talking about, a part out of a whole, we're interested in some percent, and that's what's in question, it's automatically a Z test every time. You don't have to ask yourself about the population standard deviation at all. So to actually find those test statistics, if it is a mean-based problem, then we're going to solve for T or Z, and it's actually the same formula between the two, which seems a little weird, but the number you get at the end of it, whether or not it's a T or Z, is going to be used differently down the line. That does end up giving you a different answer, but just kind of to get the test statistic itself, it's just going to be called Z or T based on what we just discussed above. But if it's a mean-based problem, you're going to solve for that by doing x bar minus mu divided by s divided by square root of n, where x bar is the mean of the sample, mu is the mean of the population, S is your sample standard deviation, and N is the number of trials in your sample. So that's what you do given a mean-based problem, but given a proportion-based problem to find the T or Z test statistic, where actually it's a little bit more complicated, but it's still telling you the same thing, where we have sample information minus population information, so the sample proportion this time minus the population proportion, and you divide all of that by big square root population proportion times 1 minus population proportion divided by n. So just make sure you were careful about your order of operations there, making sure that you don't get any wires crossed so you end up getting the right answer. So you're going to solve for those test statistics, compare it against your critical value, and based on whether or not it's an upper tail or a lower tail, find where you might or may not fall into the rejection region and accept or reject accordingly. So we're just going to go through a quick example to sort of demonstrate that. So the information we have here is just all provided, keep in mind. So we didn't get this from anywhere. We don't know the context of the problem really. It's going to seem a little bit arbitrary, but just sort of show you the way that the formulas flow into an overall answer. So the information we have here is that we have n equals 100, x bar equals 80, s equals 5. Okay, our alpha level is 0.05. And we have our null and alternative hypotheses here, where our mu is greater than or equal to 78, and our alternative is that mu is less than 78. So to sort of start off with, based on what we just went over, we're going to try and find our test statistic first, which is either going to be a z or a t. Okay, so for a mean-based problem, we're asking ourselves, okay, is this z or t? Well, it is, first of all, a mean-based problem because the information we had right here was all mean-based. We have x bar, which is your sample mean. We're hypothesizing about mu, which is your population mean. It's all mean-based for sure. So under the 4 mean-based problems, that's where we're looking. We ask ourselves, do we or do we not know the population standard deviation? Well, based on what we have right here, we don't have any information about a population standard deviation. We have our sample standard deviation up at the top right, the s equals 5, but we just simply don't have anything to indicate whether we do or don't know the population standard deviation. So let's not assume we do and still say we don't know it, in which case we are using a t-test. So you can see right here we have a t-test, and the way you're going to solve for that under a mean-based problem, like we talked about above, is x bar minus mu divided by s divided by square root of n. So I simply plugged in x bar from my 80, 78 from my mu, which is what we were hypothesizing about. So you can see the HO, mu greater than equal to 78, so on. That's where we get the mu from right there. And we're going to divide that by the provided standard deviation of 5 divided by square root of 100, which is our n. So once you solve for that, you're going to get about 2.53, and that is going to be your t-test statistic. So at this point, we have our t-test statistic so that we can compare it against a critical value, then accept or reject accordingly, but we actually have to find that critical value. So reference the chart that I showed you just a moment ago, and we're going to look to see how we can drill this down to actually find out whether or not we're dealing, or which Excel function to use so we can plug into it and get our critical value. So here we're clearly dealing with a one-sided critical value because up at the top when we're talking about our hypotheses here, you can see that this is a one-tailed consideration. We're talking about one direction only. It's not equal to, then not equal to, which would be a two-tailed test. We're dealing with a one-tailed test here. So I know I'm going to look at the top part of the chart, the one-sided critical values. This situation is going to be a t-test because everything we just talked about, we know that we do not know the population standard deviation, which would indicate it's a t-test. We just solved for t. Everything right there screams t-test. So look at the two bottom parts on t-test right there, leads you to your alternative hypothesis saying whether or not we're dealing with a one-sided upper tail or a one-sided lower tail. Well here, if I'm looking at the alternative hypothesis, you can see that the inequality we put right there is a less than symbol, meaning that we're dealing with a one-sided lower tail. So simply it's a t-test using one-side lower tail. So when you look at the associated Excel function dealing with that, it is t.inv alpha, comma, degrees of freedom. So you're simply just going to type this into Excel, go equals t.inv, a function will pop up, click that function, you're going to fill in 0.05 for your alpha because that was given information up at the top right here. We were given that our alpha was 0.05. So you put that in, and then our degrees of freedom, that is simply going to be n minus 1. That's pretty much universal rule. So we can see that our n up here was 100. So 100 minus 1 is going to give us 99. And when you plug that into Excel, and it's not going to be the exact answer, but approximately negative 1.66 is our critical value on the lower side. So finally, to decide whether or not you accept or reject this, what's going on is that that negative 1.66 is the critical value. It's the threshold that begins the rejection region. And since we're talking about the lower side of it, we're saying that in order for us to reject this hypothesis, our critical value that we determined, this t-test statistic right here, has to be less than your critical value to fall into that rejection region. Well, you can see that 2.53 is certainly greater than negative 1.66. So if it's the case that it doesn't fall into the rejection region, you're actually not going to reject this hypothesis at all. You're going to accept it. So just kind of overall, you have to make sure that you can read that chart. That's very important. There are a lot of different values on it, but you need to treat it step by step. So start with whether or not it's a one-sided or two-sided critical value. Find your test statistic based on the notes we have, then decide your alternative hypothesis. That will lead you to the Excel function. Compare what you get from that Excel function, which is going to be a critical value. Compare that to your test statistic, and then based on whether or not it's a lower tail or an upper tail, see if the test statistic falls into the rejection region. If it does, reject it. If it doesn't, then don't. So thank you so much for watching, and I hope that helped.